Welcome to this video in which we will analyze an inverting op-amp circuit and show you how to use it to create a circuit that has gain as well as changes the sign of the input. That is, the output will be some multiple of the input but with a negative sign. So let's begin. We'll do this analysis using the ideal op-amp model. And as we've talked about in previous videos, the idea behind the ideal op-amp model is that the current going into the inverting input and the current going into the non-inverting input, both of these I minus will be 0 and I plus will be 0. This is both of these are consequences of the fact that in the ideal model we assume the input resistance is extremely large. Okay. And secondly, we will assume that the voltage at the inverting input is equal to the voltage at the non-inverting input. And again, the rationale for this is that the output of the op-amp, this point here, the op-amp will do whatever it has to create the voltage here that will make sure that the voltage at the inverting input is equal to the voltage at the non-inverting input. And again, the way you justify this assumption is the idea that the gain is very large, so in real life the difference between these two voltages has to be very small. So with those two assumptions, let's see if we can solve this circuit. Okay, first we'll look at figuring out what V plus is. Well, V plus is connected down here, and I should have pointed out this is our ground node or our reference node. So V plus is connected to ground, so it's equal to 0 volts. Okay, which means then that V minus will also be equal to 0 volts because we're making this assumption due to the ideal op-amp model. So this node in the circuit is at 0 volts. Okay, the difference between here and ground. Okay, so that allows us then to fairly easily compute the currents that flow through R1 and RF. If I call this I1, the current that flows through R1 will be equal to this input voltage, VI, divided by R1. Okay, and again, the reason for that is the voltage at this point is 0 volts, so the voltage across R1 is just the same as VI. Okay, so that gives us I1. Let's see if we can figure out IF. Okay, this is the current through RF. So again, I have that the voltage at this point is 0, because again V minus is equal to V plus is 0. The voltage at this point is V0. So IF is equal to V out over RF. Okay, now we're almost done. We almost have everything we need to get the relationship between the input voltage and the output voltage. And the way we can do that is apply Kirchhoff's current law at this node. We have I1 coming in, so Kirchhoff's current law at the inverting node says I1. We also have IF coming in, and we have I minus, this guy here leaving, but we've said that I minus is equal to 0, so there's no current there. So basically I1 plus IF is equal to 0. Well, we can substitute in for I1, and we have VI over R1 is equal to minus V out over RF. So I've just taken this IF and moved it over here and then plugged in values. And solving this for V out, we can then say that V out is minus RF over R1 times Vn. So there you have it. We've basically solved what the output of this op-amp circuit is for any input voltage and any combination of RF and R1. So let's talk about this just a little bit. This term negative RF over R1, this is called the gain of the circuit. So I could say gain of circuit. And the idea is it tells us how much V in is increased to get V out. And in this case, the fact that the gain is negative means that V out will have an opposite sign to V in, and it'll be multiplied by RF over R1. Okay, so this is how you do the analysis. Now, quite often, you won't be asked to analyze a circuit, you'll be asked to design a circuit. So suppose someone comes to you, given your extensive background in circuits, and says, I would like you to design an inverting amplifier with a gain of, say, -7. Okay. Well, then what we would do is we would start with this circuit, that is an op-amp connected with R1 and RF as shown. We could arbitrarily choose a value for R1. So let's choose R1 is equal to 1 k ohm. Okay. Then to get a gain of -7, we would need the ratio between RF and R1 to be 7, which says that RF would be 7 k ohms. Okay. So that's pretty much all there is to doing this design. Now, one question you might have is, how do we actually choose a value of R1, since once we choose R1, then RF will be specified? And we typically do that by looking at the typical ranges of the input voltage, looking at the specifications of our op-amp to see how much current it can source, looking at how much current we're willing to let flow back through RF, because that's going to be that's a power drain, and so on. So you size R1, and from that RF, taking into account current and power consumption and so on. For a typical op-amp application, R1 of 1 k ohm is a pretty good first guess, typically. But again, you'd want to make sure that you've got it right. So, hopefully this explains or helps you understand better how to do analysis of op-amp circuits. We've introduced the concept of gain. We've discovered that gain can be negative. It just changes the sign of the output relative to the input. And I think we'll let it go at that. So thanks for watching.